Hello and welcome to this lecture. So, we saw the easier case of compositions so far, right. So, when we are looking at S composed with T, if rank of S is 2, rank of T is 2, both of them are 2, we saw some very easy ways to characterize the range and the null. Okay. So, now I am going to ask this very interesting sort of question which will give us a fascinating picture of this composition. When is the composition equal to 0? When is S composed with T equal to 0? Okay. As in, when will the range of this S composed T be just the origin? When will the null be the plane, right? So, the very obvious answer that all of you will think of is the 0 case. S has to be 0 and T has to be 0, right? So, that is very obvious, it is very clear. If either S is 0 or T is 0, then the composition is definitely equal to 0, okay. Now, let us look at our simpler cases from earlier. Supposing rank S is 2, okay, so S becomes dimension preserving, which means S composed with T will be 0 if and only if T is 0, there is no other possibility here. So, rank S is 2 seems to suggest that T equal to 0 is the only possibility. If rank T is 2 also, okay, then S composed T will be 0 if and only if S is 0, because T is dimension preserving. Anything you put on T, it will give you something with the same dimension, right. So, that goes through. So, if S composed T has to be 0, S has to be 0. This seems to suggest maybe the 0 is important, but we are losing out on one important possibility, right. What can happen if rank S equals rank T equals 1? This turns out will provide you very, very interesting cases for S cross T equal to 0. Okay. How is that possible? Let us look at that now. Okay. Here is an example. Okay. This is an example with rank S equals rank T equals 1. Okay. This is example 1. So, S is represented by 1, 2, 0, 0. Okay, this is one matrix. T is represented by 1, 2, 2, 4. Okay, notice clearly the rank here is 1. Here also rank is 1, right? 1, 2 and 2, 4 are linearly dependent. If you multiply 1, 2 by 2, you get 2, 4. So, both of them have rank 1. Okay. If you now look at S composed with T, it is represented by the product of these two, right? And if you multiply 1, 2, 0, 0 by 1, 2, 1, 2, 2, 4, you get 5, 10, 0, 0. Okay. So, here is a rank 1 case and a rank 1 case for S and T, and their composition is non-zero. Okay. So, you might say, okay, this is dull, boring. I mean, what is the big deal in this? Turns out, here is another example where S is represented by the same 1, 2, 0, 0 and T is represented by something else here. So, I have cleverly picked this. So, you can see it is minus 4, minus 8, 2, 4. Okay. I have changed the 1, 2 to minus 4, minus 8. Now, notice what happens. Here is the surprise result. S composed T is represented by this product, and that product ends up being 0, 0, 0, 0. You can multiply and check if you do not believe me. 1, 2 minus 2, 4 is 0. 1, 2 minus 8, 4 is 0. Okay. So, here is this surprising property with matrix multiplication or linear transformation composition. S composed T can be 0, but S is not 0 and T is not 0. Okay. And this happens because this rank S and rank T are 1. If that were not true, this won't happen, right. So, we know that also, and you can see rank of T is also 1. Hope you see that, because minus 4, 2 when multiplied by 2 will give you minus 8, 4. Okay. So, this is rank 1. So, there are two rank 1 matrices and they behave in this strange fashion. So, product of two non-zero matrices can be all zeros. Okay. So, this complicates our study of compositions, and one needs to pay attention to this particular case. Interestingly, in this example, if you do T composed with S, as in if you multiply this matrix the other way, okay, put 4, minus 8, 2, 4 and 1, 2, 0, 0, you get the same as this matrix. Do you see that? You get the same matrix as this. So, this matrix times this matrix gives you this first matrix again. Okay. So, all these nice, very strange sort of properties are true for matrix multiplication, and these are very, very different from your regular number multiplication, right. If you multiply two numbers, if the product of two numbers has to be 0, one of those numbers better be 0, right. But in matrices, that is not true. In the 2 cross 2 matrices, you can have two matrices multiplying to give you 0, but if you multiply the other way around, they will give you something non-zero. So, all these kind of strange things can happen with 2 by 2 matrix multiplication, and this is what makes composition very, very interesting. Now, let us look at this in slightly more generality. Okay. For that, we have to understand these rank 1 transformations a little bit better. So let's start with a linear transformation T, which has got a matrix A, maybe in the canonical basis. Okay. So what does it mean to say, linear transformation T has rank 1, matrix A has rank 1? The range of T is a line through the origin. Null of T is also a line through the origin, right? Null has to be rank 1, range should also be rank 1. When you say, null has to have dimension 1, range should also have dimension 1 when you say rank 1 and nullity is 1, right? Because it's 2 cross 2, okay. So dimension 1 subspaces are lines through the origin. So range T and null T have to be lines through the origin, okay. Columns of A will be linearly dependent, right? The two columns of A will be linearly dependent. Only then you will have rank 1, okay. Maybe one of the columns will be 0 and that also makes it trivially linearly dependent, but this is linearly dependent. Same thing with rows of A. Rows of A should also be linearly dependent, okay. So this is what we know about rank 1 transformations, okay. So let me pictorially represent that for you. So when R2, entire R2 goes through a rank 1 T, you get a range which is a line through the origin, and null is a line through the origin. There is one special line through the origin which when it goes through T, you get the origin entirely, okay. So here are examples. Rank 1 can look like this. So range is y equals 0, okay. Do you see that? Do you see why range is y equals 0? So if I do all possible linear combinations of the columns, I will always get y equals 0, okay. And x can be anything. So that will go through the entire x-axis. So this gives you the x-axis, okay. So y equals 0 is the x-axis, and 1, 2, 0, 0, all column space is the x-axis. What is the null space? Okay, the null space is x plus 2y equals 0. So this is very trivial, okay. So how do you think of the null space here? I'm doing 1, 2, 0, 0 times xy equals 0. So this is equivalent to x plus 2y equals 0, and this is the null, okay. The range is, what is the range? Range is 1, 2, 0, 0 xy for all xy in R2, okay. That is the same as set of all x plus 2y comma 0 for all xy in R2, okay. So now this needs a little bit of thought, but you can see when you go to all xy in R2, you are getting y being 0, okay. So this may be any point. So this is nothing but the x-axis or the line y equals 0, okay. So if you want to picture this guy, okay, so if you want to picture this linear transformation, what is the range? The range is this guy. This is the range, y equals 0. What is the null? X plus 2y is 0. So which is y is minus x by 2, okay. So it will look something like this. This is the null, y is minus x by 2, okay. So whatever point you take here, if you hit it with this linear transformation T, 1, 2, 0, 0, you will get some point on the x-axis, okay. If you take any point on this null, you will go to 0. Any point on this null, you will go to 0, okay. So this is a good way to picture this kind of rank 1 linear transformations. Okay, I think I wrote that wrongly here. Let me write down carefully. This is range, that's null, okay. So all these guys go here. I hope you can picture this. This is how you have to picture it. The range is the x-axis, okay. Any point will come to the range, okay. So if you're here, you will come to the range. If you're here, you will come to the range, okay. If you end up on the line, you will go to, on the null line, you will go to the origin, okay. So this is the way to picture it, and I hope you see how to find the x-axis here. Another way of doing it is to elimination with the columns, right. So you would start with 1, 0, 2, 0, okay. This is row 1, this is column 1 and column 2, okay. And then you do elimination. So you can do column 2, set it as column 2 minus 2 times column 1, and you end up getting, if you do that, you will end up first column as such, you will get 0, 0 here. So you can throw this out. So the range is the the basis for column space is 1 0, and that gives you x axis again. Okay, so there are various ways of doing range and null. I hope you can see that here. Okay, so that was a very simple example. Let's see a slightly more complicated example. Okay, 1 2 2 4. Okay, so I'm going to do it sort of in my head now. Okay, so if you take the first column, eliminate the second column with it, you will do column 2 minus 2 times column 1. So you will end up getting 0 0 here. Okay, so the range, the basis of the range is just 1 2. Okay, all products of 1 2, and that is same as the line y equals 2x. Do you see that? 1 2, right? All multiples of 1 2, that is same as the line y equals 2x. Okay, so this kind of converting the range in a one dimension, in a rank 1 transformation from basis product to the range is a important enough idea. I hope you can appreciate that. Okay, what about null? Null is this matrix times xy equals 0. So you get x plus 2y equals 0. Null remains same as the previous matrix. Okay, very interestingly. So you get just x plus 2y is 0. 2x plus 4y is 0 is also the same as x plus 2y is 0, right? So you only get one thing. So this is the range, this is the null. Again, 2 lines, right? Always this will be true for a rank 1 2 by 2 matrix, right? The range will be a line, null will also be a line. Here is another interesting case. Okay, so you might think of this. Minus 4 minus 8 2 4. Okay, this is interesting. This played a role in our previous example, and you'll see why this kind of matrix is curious. Okay, so it's got a curious little property. You'll see how it ends up in being useful. If you do elimination, what do you have to do? You will do minus 4 2, okay, minus 8 4. So you eliminate the second column. You again do column 2 minus 2 times column 1. You will end up getting 0 0. So the basis vector is minus 4 2. What is minus 4 2? X is minus 2y, right? All products of minus 4 2, I mean all linear combinations of minus 4 2, all scaling of minus 4 2. That line is the same as x being minus 2y, but x being minus 2y is the same as x plus 2y is 0. Okay, I hope you saw that, x plus 2y is 0. So range became x plus 2y is 0. Here is a curious little property of this minus 4 minus 8 2 4. Okay, notice this. If you were to find null, you're going to multiply this with xy and equate to 0. You get minus 4x minus 8y is 0, or 2x plus 4y is 0. Both of them are equivalent to x plus 2y is 0. So here is this curious property for this strange little matrix we have here. The range and the null are the same. Okay, so what does that mean? X plus 2y is 0 is both the range and the null. Okay, so how does that work? You might think I'm pulling a fast one on you. What is going on here? Okay, so it's not a fast one. Let's say this is x plus 2y is 0. Okay, this is my null and range. So what does that mean? If I have any point here, I will end up in on the range. Okay, so any point here, right? Any point, I'm just trying to see, make sure I get the quadrants right. Both the negative will be here. Okay, so any point here, I'll end up here. So whatever point I take, right, I'm going to end up on these things, on this line. Okay, so on this range. Is that okay? So the range is a line there, and whatever point I pick in R2, I'm going to end up in my range. Okay. Now what happens if I pick the point on the range itself? Then I will end up in 0. Okay, if I pick this point here, I will end up here. That's what this transformation does. Okay, so it's not impossible to imagine, but range and null are the same thing in this matrix. Okay, so I hope you get a sense of these rank 1 transformations. They can be a bit confusing, but they're very easy at some level. I mean, 2 by 2, it's very easy to think of rank 1 transformations. Okay, so now what happens to the composition? Armed with that idea, let's jump into the composition. So you have R2 going through T and you get range T. Okay, so when you compose S cross T, that has been our picture always, right? We start with R2, go through T, go to range T. If you want to find range of S cross T, this is what we do. Now range T is dimension 1, is a line through the origin. Okay, Now when it goes through S, I'm going to get range S cross T, S composed with T, I'm sorry, range S composed with T. This is okay, the same as before. But what can I say about the rank here? What are the different cases here? There are two cases. Case 0 is range T equals null S, okay. So range T equals null S. In case range T becomes the same as null S, remember null S also is a straight line, right? Null S is a straight line, dimension 1. Range T is a straight line, dimension 1. Supposing null S becomes the same as range T, right? Guess what? Your range will become 0, okay. And this is what was going on in our case where when we had two non-zero matrices multiplying to give you 0. Okay. So, when range of T has dimension 1, but if it ends up coinciding with the null of S, which is also a dimension 1 space, then the range of S cross T can be 0. Okay. There is another case here when range T is not equal to null of S. Supposing this line and the line which is null of S intersect only at the origin, they do not intersect anywhere else. If that is the case, then range S cross T will be range of S. That line that S has will be the thing. Okay. So, these are the two interesting cases, and notice how the range becomes 0 because of the strange coincidence, and this can happen whenever only when the dimensions are the same, right. Range T and null S have to have the same dimension and they have to coincide like that. We can come up with very interesting examples for that. Here are examples that I put down. Null and the range coincided, and of course here strangely enough the null also coincided, but that is okay, but range and null coincided. So, S composed with T became 0, okay. So, range of T became equal to null of S, okay. But the other way around is not true, right. The range of S and the null of T are different, so you get non-zero things, okay. So, I hope this is clear to you. This is the way in which non-zero operators compose to give you 0 operators, okay. I hope that was clear. It is an interesting little curious property that two non-zero matrices can multiply and give you 0, and that happens because of this curiousness of the dimension being the same for range and null, and you can make both the subspaces the same, okay. Thank you very much.